Electra synchrotron light, for example, in Trieste, Italy is a beautiful lighthouse, beautiful place to work. In Beijing, also in Taiwan, several places. There are about, I would say, around 30 synchrotron around the world, and then all this facility are building bigger and bigger ring, and people learn how to store electron beam and positron beam, and how to capture photons and monochromatize the photon to do a very nice experiment that simply cannot be done with laboratory light source because of the intensity of the rays. Rather exciting thing to work on with the synchrotron. And you can do it in Canada with the Canadian light source. Okay, so let me switch gear about the last technique that I want to talk about before we move on to the electronic structure, which is also a technique invented in the mid-80s, 1986, before 1986 or so, by two IBM people at Surge IBM. They were looking at these a technique called what they call scanning tunneling microscopy. So it was a very fast-growing, what I call fast-growing surface analytical technique, which is trying to replace low-energy electron diffraction as the tool, but as you'll see later, it can never replace LEAD if you understand what STM is giving you, because it holds different type of information, and STM, once people start using it, would have discovered its limitation. Okay, so let me describe. It is one of the stable, the so-called real nano tool in the way that it can image the electron density of a single atom. So this is the power of these. This is the first off the gate, if you like, the physicists come up with this idea of nano tool, and later on, of course, the IBM group at San Jose in California, they have used a similar technique, a tip-based scanning tunneling microscopy technique, to move atom, to actually use it to pick up atom and move it around to construct artificial nanostructure, what they call micro-machining or nano-machining, creating nice physics, primarily for physics because of quantum mechanics, looking at quantum mechanics that way, using this type of approach. So what is STM? So the STM, how does it, what gives rise to STM? The reason why the IBM people can come up with this is because of material science, because they discovered that there's something called piezoelectric. Okay, piezoelectric is a ceramic. It's a piezoelectric material is something that if you apply a voltage, it will stretch, right? It will extend its length. Okay, it is known as one of these smart materials, so-called smart materials. So a smart material is something that responds to a stimuli, and in this case, the stimuli is a voltage. And if you apply a voltage, this ceramic, piezoceramic, will stretch. Okay. So why is that important? Well, because with piezoelectric, you can actually apply a small voltage and stretch, and the material only stretch in a very small way, in a tiny amount. Okay. So now this enables you to position your tip very, very close to the surface that had never been done before. Okay, so typically then in a scanning tunneling microscope, what you got is that you have a tip, right? And we'll talk a little bit about the tip. The tip is something that you try to make it as sharp as possible, preferably with one atom at the apex of this tip. Now, making the tip is not an easy thing. There are ways to make this. And if you can make a single atom tip, right, this is called a single atom, atomically sharp tip, and if you can position this tip atom very close to the surface, then what will happen? According to quantum mechanics, is the two wave function, the wave function of this atom, and the wave function of your tip atom, and the wave function of your surface atom will overlap. Okay, and if it overlap, that means that you can share electron density. Okay, so in other words, if you position so close, then there will be tunneling occur between your sample and your tip atom like this. So the wave function overlap, it means that you're sharing electron density across like this. And the reason why you can position so close is because of the invention of this piezoelectric material. And so what they have is that they have essentially two set of piezoelectric, an X set and a Y set, right, like this is shown on these. This is a looking down version of this column. So you have X and Y, and you can apply the voltage. You can mount your tip on here, so you can pull and push, if you like, on this column, and then you can move. Right, you can scan in the XY direction depending on the voltage you apply in the X piezo or the Y piezo. Okay. Now to move it close, you have a third column in the Z column pointing out of the plane. So this is this vertical one, and you can also apply a voltage to that, and then you can extend, right, by tuning your bias. You can extend your tip or withdraw your tip. Okay. And so this is great because now you can position your tip atom very close, incredibly close to the surface, such that wave function overlap will occur, and therefore tunneling phenomena will occur. And the third, so this is piezoelectric in terms of instrumentation. That's the first thing. First thing is that you have to make a very sharp tip. Second thing is that you have to have piezoelectric. And the third component is that you've got to have good feedback electronics so that you can control the motion of this. You can measure tiny amount of current, usually picoamp current on this on this tiny little current that go through between these two. Okay, and so that you can scan across. And of course, something that's not in this picture is that you got to have extremely vibration-free platform for this microscope to work on. You cannot, my voice, just like that, will affect the vibration. The acoustic voice will affect the noise picked up by this tip. Okay, so you have to be in an extremely quiet both electronic and audio and vibration-free environment in order to image this. Because you can imagine this separation is of the order of angstrom, right? So you have to position it close enough, a few angstrom separation, so that you can tunneling can occur. It is quite amazing, in fact, right? Because you can imagine that how could you position something so close, and piezoelectric is the answer, is that allow you to do this. Okay, so this tunneling, there's an article that you can read about. So let me just describe. This is in an article that we'll point out later. So the idea was that if you can somehow position the metal tip atom close enough to the surface atom of the order of a few angstrom, then quantum mechanics said the wave function of the tip atom and the surface atom will overlap, okay, leading to the so-called quantum mechanical tunneling phenomena. This is well known. So tunneling is known for 50 years since the invention of quantum mechanics in the 20s. So it's no big deal, but this is the first time actually people in the early 80s, first time that people actually can make tunneling occur artificially like this and actually use it for something useful. And of course, they were awarded the Nobel Prize in Physics in 1986. one of the fastest Nobel Prize awarded within